Welcome to lecture number 11 for ECE476, Advanced Embedded Systems. In this lecture, we're looking at motors with analog inputs. Bit of background, this is a lecture that's in Bison Academy. That is the unofficial website for the Department of Electrical Computer Engineering at North Dakota State. This is 476 Advanced Embedded. A course that looks at using Raspberry Pi Pico along with Python and a GeeekPi development board that's got a nice graphics interface. And right now we're at number 11, motors with analog inputs. Now the previous lecture we looked at motors with binary inputs. Those tend to be smaller motors, like 1 watt, 5 watt, 10 watt motors. Today we're going to be looking at motors like this. This is a 100 watt DC motor from Clifton. This is a 300 watt AC motor. Kind of tell it's AC. It's got 3 leads. Well, these right here. Those are the 3 leads coming in. 3 leads tells you it's not DC, it's AC. This is a 2-lead motor, DC. Now, 300 watts is something to have some respect for. A Tour de France athlete, for example, outputs 300 watts on average, so that's actually quite a bit of power. In a burst, a Tour de France athlete can output 1,000 watts, about the size of this motor. So have some respect when talking about 100 watts, 300 watts, 1,000 watts. Another way to look at it, a horse outputs 1 horsepower about. 1 horsepower is 641 watts. A horse can beat the crap out of a person. So when you're talking about 600 watts, have some respect. Now, one problem I'm going to run into is, where are we at? There we are. If you're going to drive a motor at 300 watts, you need a power supply capable of 300 watts. The power supply on the Pi Pico boards, it's these guys right here. This is the one of the Pi Pico boards from GeeekPi. This uses the USB port. The USB port is only good for 2 amps. 5 volts at 2 amps is 10 watts. You can't drive a 300 watt motor with a 10 watt power supply. You need a bigger power supply. Well, those are available in many different places. The place that I like is Marlin P. Jones. What Marlin P. Jones does is they buy surplus. So if a company goes out, buys 1,000 power supplies, only needs 700 of them, the other 300 they surplus, Marlin P. Jones buys them and sells them to you for a big discount. So if I go under power supplies, you've got your benchtop, DC, AC. If you don't need a lot of power, I can go with one of these. So here's 12 volts, 6 amps, 70 watts. If you need more power, I can go to a benchtop power supply. This will output 14 volts at 2 amps, 30 volts at 10 amps, 300 watts. So that's kind of one place to go if you need more power. Here's one of the power supplies. The other option is if you're a student in the Department of Electrical Computer Engineering at NDSU, we've got the power supplies and labs. Otherwise, if you want to get your own, here's one place to go. So anyway, back at the ranch. This is lecture number 11 for 476, as I was saying. So in the previous lecture, again, we looked at low power supplies. These are motors, or low power motors. These are motors with binary inputs, digital inputs, like stepper motors, BLDCs, DC servo motors. Larger motors tend to have analog inputs. So this lecture looks at how to drive 2 different types of motors. A DC servo motor, specifically a 6 watt and 100 watt DC servo motor, and a 300 watt 3-phase AC synchronous motor. So let's kind of start out. The basic motor would be an AC motor. If you take a magnetic field and have a coil rotating inside that magnetic field, as the coil spins, it outputs a sine wave. If I throw in a commutator, that's these brushes, what happens is the coil spins, it just picks off the peak, and then it flips the connections, and I get another peak. That gives you a half wave or full wave rectified sine wave. Converts AC to DC. So that's kind of the idea behind a DC motor. DC motors are also generators. called dynamos. And that's actually how the DC motors were discovered. They were being used as dynamos, and people noticed that the generators spun by themselves when you connect them to power. Generators and motors are one and the same. Now there's a couple different types of DC motors. If you go to Amazon, you can buy these smaller motors. This is a 12 volt, 500 milliamp motor. It's a gearhead motor. There's a small DC motor over here, and this is a gearbox. What the gearbox does is it slows down the motors. Okay, motors are designed to spin, so this motor can be spinning quickly, whereas the output shaft is spinning fairly slowly. This would be for driving something like a robotic arm, or opening and closing a valve. A robotic arm doesn't need to spin at 300 RPMs. I just wanted it to come over, pick up something, set it down. So that's what the gear does. What the gear does, it slows down the motor and provides more torque. For this motor, it draws 500 milliamps and 12 volts. Well, that's more than a Pi Pico can output, so I need a buffer circuit. The buffer you need depends upon what you're going to do with the motor. If it only spins in one direction, all I need is a transistor. So if I want to just have the motor spin forward, I'll have the motor connected from 12 volts to ground. It spins. Break the path to ground with a transistor. Then the Pi Pico can turn the transistor on and off. If I pick my favorite transistor, I kind of like ZTEX transistors. This has a gain of 300. So to get 500 milliamps flowing here, I need at least 1.6 milliamps at the base, or 2.6 milliamps at the base. Pick RB so that IB is bigger than 2.6 milliamps and less than 12 milliamps, because that's all a Pi Pico can output. So that means pick RB anywhere in the range of 216 to 975 ohms. I chose 220, 330 works. Anything in that range works. What that does is now when the Pi Pico outputs 3.3 volts, or logic 1, the motor turns on. When it outputs 0 volts, the motor turns off. Okay, so let's see how that works. Here I've got a Pi Pico board. This is the $14 version, similar to the one that we're using. The output goes on pin 18. Here I've got 4 NPN transistors because I borrowed one from before. Anyway, I got an NPN transistor, turns it on and off, and my DC motor. If I connect the motor between power and ground, side light, the power supply I'm using is a wall plug that's 12 volts, 2 amps. So I'm going to output 24 volts. Take my motor, that's these two leads right here, connect them between power and ground, and the motor spins. Okay, so now that the motor works, I'm going to add the transistor. I'm going to put the transistor between the path to ground, so the motor goes from power to the collector of the transistor. The base goes to the Pi Pico board. And then in software, I can make that pin on or off. So I'm going to turn on for 1 second, off for 1 second. And as I do that, see the motor turning on and off. And let's slow it down a little bit so you can see it. On for 3 seconds, off for 3 seconds. So off for 3 seconds, on for 3 seconds, off for 3 seconds. Alrighty, so I can turn the motor on and off. Now with this, I only turn the motor one direction. If I want to change the direction of the motor, I've got to manually take the leads and flip them. Well, that's for binary output. Suppose I want to vary the speed of the motor. Well, I can do that with pulse width modulation. I can go from 0 volts to 100% to 3.3 volts to 0. For the transistor, I can't do that at this point. If I make this something like 1.5 volts, that doesn't really work. This is set up as a switch. 0 volts is off. 3.3 volts is on. If I apply something in the middle, I may or may not be saturating the transistor. It's probably in the active region When it's in the active region, this dumps heat. It gets hot, it's going to burn out. Basically, these transistors, you can tell these are designed for binary outputs. They're too small to dissipate heat. So you're not supposed to use those in the active region. So to make this run at half speed, what I'm going to do is instead use pulse width modulation, turn the motor on, then off, on for half the time, off for half the time. It looks like it's on 50%. Vary the duty cycle from 0 to 100%, and I can vary the speed. So here's what that looks like in software. I'm going to use the PWM module from machine. I'm going to define pin 18 to be an output at 1 kilohertz. The duty cycle is going to vary. Starting out at 0% duty cycle, motor's off, I'll have a lookup table. This is outputting a half rectified sine wave. The peak is 65,000, 100%, with 200 entries. The first 100 is your half rectified sine wave. So this is from time 0 to 100, and there's 200. I'll then spin through that table. In the main loop, every 30 milliseconds, I go to the next entry. This sets how fast you go through the table. Spin through the table, there's your output. And what that does is when I'm at 0, it's off. It slowly speeds up and then slows down. That way I can vary the speed of a DC motor. And that was the PWM code. Okay, so that's if you want a motor to run in one direction, I can just use a BJT switch. Suppose you want a motor to go forward and backwards. Well, in that case, I need a different circuit. The circuit you need there is an H-bridge. What an H-bridge does is I'll make the motor right here. If I turn on T1 and T4, current goes this way. That would be motor spinning forward. If in contrast, I turn on T3 and T2, current flows this way. So we make the motor go forward and backwards, or relative to the motor. If I have a 10 volt supply, actually I have a 12 volt supply, I can apply plus 10 volts or minus 10 volts across the motor. I can get a plus minus power supply, plus minus voltage to the motor using a single power supply. Now, H-bridges you can build, or for about $2, just buy one on eBay or Amazon. Just search for L298N on Amazon. This is an H-bridge capable of 2 amps, which for me is fine because all my power supply will do is 2 amps. If you need more power, just get a bigger H-bridge. What this one does, to wire it, this actually has 2 H-bridges in it. The first H-bridge, on the left-hand side, has the 2 inputs that controls it. To power the H-bridge, I need 5 volts in ground. That powers the electronics on the H-bridge. I need common ground and my power. This is your 5 volts to 35 volts at up to 2 amps for this H-bridge. And one motor goes on the left, one motor goes on the right. I just have the one motor. The inputs come over here. So the left 2 control the left motor, the right 2 control the right motor. In terms of software, if I set pin 17 to ground, to 0 volts, and 16 as a PWM, the motor spins forward. If I send 16 to ground and do pulse width modulation on 17, the motor goes backwards. So by flipping between the two, I can make the motor go forward, 0 to 100% speed, reverse, 0 to 100% speed. Now to see how that works. Okay, so let's see how that works. Here I've got 2 output pins, forward and reverse. That's pin 16 and pin 17. They're both PWM outputs at 1 kilohertz. And you kind of hear that 1 kilohertz whine. That's the 1 kilohertz PWM that you're hearing. I'm going to have the speed be a sine wave, goes plus minus 65,000. Then forever and ever, I'll spin through that table If the speed is positive, I'll drive pin 16 with PWM, 17 off. If it's backwards, do the opposite. 17 is the PWM, 16 is off. What that looks like is this. You see the motor spinning, going faster and slower. It stops, goes the other way. And you might hear a 1 kilohertz noise. That's the 1 kilohertz PWM. If I drop that frequency, say 100 hertz, it's more of a low frequency hum. But now the motor is turning on and off 100 times a second. With the motor inertia, motors are usually designed to drive something. I'm going to add a flywheel or wheel, something over here that has inertia. That'll take care of the 100 hertz on and off. Another thing I could do, if I measure the voltage across the motor, you can see that the DC voltage, voltage going to the motor, is going up to 10 volts, coming back down. It's now minus 10 volts. So there's your plus minus voltage. I can get a plus minus voltage, make the motor go spin forward and backwards, using an H-bridge with only a single power supply. So this is using a 12 volt, 2 amp motor, 24 watt motor, plus a 12 volt, 2 amp power supply. You can use the same idea to power bigger motors. For example, if you go to Amazon or eBay, here is a 1000 watt, 36 volt motor, same idea. This is designed to drive a scooter or electric bicycle. And you can get bigger ones. Again, for not a lot of money, 86 bucks, you can get 1.5 horsepower. Now to drive that motor, I need a switch capable of 30 amps and 36 volts. BJT transistors typically don't do that, but power MOSFETs can. Basically, a MOSFET will outperform a BJT transistor. We don't normally use them in lab because they're static sensitive. This is what's inside the MOSFET. A MOSFET is a small insulator over, now let's draw it like this. I've got a N-channel, N-channel, P-channel substrate. Here's the drain, here's the source, here's the gate. And usually the substrate and the source are shorted together. If I take this tied to ground, then there's no current flow drain to source because this is a reverse bias diode. If I apply a plus voltage at the gate, like plus 10 volts, that attracts minus charges to the surface, and I get an N-channel. They're now shorted together. For this MOSFET, if I apply 10 volts VGS, the resistance becomes 5.9 milliohms, basically zero. So this is just a great switch. It's capable of 57 amps, which is pretty impressive. Handles 30 amps plus for not a lot of money. I think it's like $2-3 bucks. The problem with MOSFETs, they're static sensitive. If I apply like 100 volt static gate to source, I'll punch through this insulator and I destroy the MOSFET. So MOSFETs are static sensitive, which is why we don't use them in lab. If you're in industry where they've got better control over static, they're actually used instead of BJT transistors. Cheaper, higher current capability, no current draw, basically no current draw at the gate. So overall superior. If I want to take or interface a 1000 watt motor to my Pi Pico, I need something like a power MOSFET. So picking one, kind of at random, here's a nice one, capable of 60 volts, 57 amps, actually up to 95 amps, and anything less than 3.7 volts turns off. At 10 volts, it becomes 5.9 milliohms. becomes a switch that can handle a 1000-watt motor. To use it, I need to have the gate go between 10 volts is on, 0 volts is off. 0 volts is easy. The 10 volts is a challenge. One way to take the PIC output and convert 3.3 volts to 10 volts is use a switch. In this case, if this is 3.3 volts, I saturate the transistor and this becomes 0.2 volts off. If this is 0 volts, this turns off. When this is off, I've got the gate tied high to 10 volts. 10 volts is on. So here 3.3 volts is off and 0 volts is on. So Pi Pico can now drive a 1000-watt motor. There is a limit to the switching time. A MOSFET is inherently a capacitor. So I've got this RC time constant. I've got, when this turns off, I charge up to 10 volts. Then when I ground it, probably goes pretty quickly, then I charge up to 10 volts. That's my RC time constant. To see how long it takes to turn on, I can calculate what is the time constant, 1 over RC. If this is 1 kilo ohm, from the data sheets, the capacitance is no more than 4,000 picofarads. RC time constant is 4 microseconds. In about 3 time constants, and this is decaying as e to the minus t over RC. In about 3 time constants, I'll be at 5%. The trains will be down to 5%. It'll be basically on. So it takes about 4 microsecond time constant. 4 of those is about 12 microseconds. This takes about 12 microseconds to turn on. So the max frequency is about 1 over that, about 83 kilohertz. So with that at 20 kilohertz, PWM should be fine. What we're doing, 1000 hertz should be fine, 100 hertz should be fine. But anyway, with a power MOSFET, I can now turn on and off a 1000-watt motor. Now that would be if I don't need the motor to change directions. It only goes one direction, like a scooter, something like that. There is no reverse. If I do want reverse, just buy a different H-bridge. For example, going on Amazon, here's another H-bridge for 16 bucks. It can drive 160 watts. That's 12 to 24 volts at up to, actually, 6 to 27 volts at up to 7 amps. If I need more power, go somewhere else on Amazon. There's this guy down here. For $19, I can do up to 60 volts, 20 amps, which is 1,200 watts for 19 bucks. So replace the H-bridge with one of these, and I can now do higher power. On this one, this is just an H-bridge, so I've got the 2 inputs that controls it. On this one, there's actually a switch. There's only a PWM input and a switch, this guy right here. Replace that switch with the Pi Pico, and I can make the motor spin 0 to 100% forward, apply 3.3 volts to the switch, 0 to 100% reverse. So that's kind of a DC motor. Next, let's look at 3-phase AC motors. Now, larger motors tend to be 3-phase AC motors. The advantage of an AC motor is there's no commutator. That means I reduce the size. And to kind of illustrate that, here is a blender motor. My blender died, so I took it apart. This is a DC motor. This is the rotor. It is, I think, 8 different coils. So I actually got 8 motors in one. One of these is energized at any given time. The other 7 are just taking up weight, taking up cost. So essentially the DC motors, I bought one, well, actually paid for 8. I'm using only one. Only one coil is energized at a given time. The outer side is my permanent magnet. It's actually an electromagnet. As this spins, the commutator, this guy right here, connects one of the coils and keeps on connecting, disconnecting it. So what that does is that takes the sine wave and just pulls off the peaks. So for the DC motor, I should get something like this. If I just pull off the peaks, I get a much more constant torque. But the cost is I've actually got 8 peaks. Pulling off one of them, I've got 8 different commutators, motors. Only one of them is being used. So the DC motor is much more expensive, heavier, bulkier, because I've got 8 motors for the price of one. Well, paying for 8 motors, using one. The second problem is the commutator. This is an inductor. Got the same thing here. Inductors store energy as 1F Li squared. When I switch out the inductor, so here's phase A, switch it out, now switch in phase B, switch it out, switch in phase C, there's current. The current stores energy in a magnetic field as I squared 1F Li squared. That energy has to go somewhere when I turn it off. What it does is the voltage goes to L dIdt, voltage goes to infinity, it will find a path to ground. So this actually produces sparks. That is the voltage shooting to infinity, finding a path to ground. Sparks jam radio signals. So the FCC will not allow these motors to be built unless you do something about the RF interference, which is part of the reason the DC motors have this big metal case trying to keep the RF energy down. Get rid of the commutator, you have an AC motor. With an AC motor, again, I don't need 8 different windings. Each winding is actually used. I don't need the big metal casing because there's no sparks, so you can just have it exposed like this guy. AC motors are much smaller, much more efficient, more powerful for the size, cheaper. To give an idea, I can buy a 300 watt AC motor for 39 bucks. I could buy a 1000 watt AC motor for 29 bucks. That's a quadcopter motor, which is pretty impressive. This is a small motor about the size of a D-size battery that's got enough power to beat the crap out of you. Yeah, it's 1.5 horsepower, so have respect. 300 watts, again, is the energy of a Tour de France athlete. 1000 watts is how much they can output in a burst. This is as powerful as a Tour de France athlete and about the size of a D-size battery. So have respect for AC motors. The problem with AC motors is the input needs to be AC. So this is actually a 3-phase motor. You can't see the leads, but it's got 3 leads. I need to have a 3-phase AC signal coming in. So I need to generate phase A, a 3-phase sine wave, phase B, a 3-phase sine wave, 120 degrees out of phase, and phase C, let's do green, a 3-phase sine wave, another 120 degrees out of phase. Generate 3 sine waves, each 120 degrees out of phase, to drive the motor. To change the speed, on a DC motor, voltage is speed, AC motors, frequency is speed. On DC motors, current is torque. On AC motors, lead angle is torque. So AC motors is a lot harder to figure out, but if you can figure it out, I go from a large DC motor down to something the size of a D-size battery. Fortunately, there are drivers you can buy to convert the DC into 3-phase AC. These are called ESC controllers. You can get them on Amazon for like 10 bucks. This one just came out in 2024. It's got your 3 inputs to the motor, these guys right here. Here's your power supply, ground, and power. This comes from your Pico board. It's actually got a couple different inputs. I can change the direction with a PWM input. I can do I2C to control it. I can do a serial interface to control it, which is pretty nifty. This just came out, so I don't own any of those. One that's been out a little bit longer, which is what I'm going to be demonstrating, is the blue one on the bottom. Let's get this out of the way. This one is the same idea. It's got 3 motor outputs, so this goes to the motor. Here's your power, ground. Actually, didn't do that right. Here's the motor. Here's your power, ground. These come from the Pico chip. The top one is 80 volts, 1,600 watts. Pretty impressive. I'm going to need to get one of those. Why? I don't know, but I know I need it. The bottom one is one I have in stock. We've had this like 2-3 years. is a 300 watt motor driver. And again, 300 watts is nothing to sneer at. That's the energy output of a Tour de France athlete, so that can actually hurt you. In terms of the signals from the Pico, if you flip over the board, here's the background. I need a 5 volt. This is actually 5 volt output used to power whatever electronics you have for your convenience. This is ground. BR is your speed input. So here's your 0 to 5 volt input coming in here. ZF is your direction. 0 volts is clockwise, 5 volts counterclockwise, and signal, that's a square wave that tells you how fast the motor is spinning. Again, this is a synchronous motor. The frequency that it outputs is the speed the motor is going at. No choice. To control this board, I likewise need a 0 to 5 volt input, or 0 to 5 volt output from the Pico board. There's a couple ways to do that. One approach, the way the board is designed, it has a potentiometer. There's basically a pot that comes with it. The pot is a resistor. One side's connected to 5 volts. That's the 5 volts from your motor driver board. Other side's connected to 0 volts, the ground from your motor driver board. And the wiper is 0 to 5 volts. If the wiper's all the way at the bottom, I get 0 volts off, all the way to the top, full speed. That's my speed control. Well, I can mimic that in hardware with electronics. There is a digital potentiometer. For example, the MCP41010 is a 10K pot with a SCI interface. I send it an 8 bits of data, 0 to 255. That sets the wiper position from 0 to 255. Connect the ends of the wiper to 5 volts and ground. Then the wiper then is the voltage out. That's my speed control. That's one way to drive this motor driver with the Pi Pico. A second option is to use the D-to-A chip, something we looked at a little bit before. Use a 4095 D-to-A chip powered at 5 volts. This will output anything between 0 and 5 volts in 4095 steps. It's a 12-bit D-to-A. By writing the serial data to the MCP4921 chip, I can control the voltage and hence control the speed. A third option that I'm going to use, PWM is just darn easy to use on a Pi Pico. So let's do a PWM output. Now, don't really want to do that directly because that'll be turning the motor on and off 1,000 times a second. Instead, what I'll do is output a 1 kilohertz PWM signal and run it through a low-pass filter. The output of the low-pass filter will pass the DC signal, block the 1 kilohertz AC signal, and likewise drive the motor. The low-pass filter, I'm going to use a second-order Butterworth low-pass filter. The gain I want takes 3.3 volts, outputs 5 volts. So I want K to be 1.56. I want the corner to be 100 radians per second. So that blocks 1,000 hertz, 6,000 radians per second. And the net result, there's my filter. Here's the circuit for it. Again, if you want to get some more background on how that works, just go to Bison Academy under Electronics. Got that corner. Go under Electronics. And this has active filters, low-pass filters, how to build them. Or DigiKey's. DigiKey's got a pretty good website for how to use stuff like that as well. Yeah, I'm fighting with my mouse, with my screen. Anyway, there's my low-pass filter. The input is the PWM signal. The output is basically a DC signal. There is ripple on it. At a kilohertz, 2,000 pi radians per second, I've got 3.3 volts peak to peak coming in, times the filter, 1.3 millivolts peak to peak coming out. So a little bit of ripple, pretty small though. That then drives the motor. A fourth option is some days somebody will have a PWM output or input, like the top one probably has it. Just buy one of those and you don't have to mess with any of this. So for the rest of this lecture, I'll be doing the low-pass filter. So here's what the code looks like. I'm just going to use pin 16 for the PWM output. For the AC motor, I just need a single PWM output. Pin 17 goes to the ZF input. That's your direction. I'll again have a sine wave, just for lack of anything better to do. I will then spin through the table. As I go through the table, the sine wave, if I'm trying to go forward, set the ZF to 0. Trying to go backwards, set ZF to 1. What that looks like is this. So here's my Pi Pico board. Again, 17 goes to ZF, 16 goes to my low-pass filter. The output of the low-pass filter goes to your speed. Okay, so now let's have some fun with the motor. Let's see what the speed is versus voltage. So to do that, here's the program. I've got pin 16 is the PWM output, 17 is the direction. I'm doing a 1 kilohertz PWM signal. This is something we're going to cover a little bit later. This is using edge interrupts. I'm going to measure the frequency of the speed output. Just take it for now that I'm measuring the speed in hertz. So as I run the code, I can display how fast the motor is spinning. I'm going to vary the voltage from -10 to +10. And if it's going forward, I'll set the direction to 0. Reverse, set it to 1. So here's what that looks like. At every 0.1 second, I'll display the time, the voltage that I'm outputting using PWM low-pass filter, and the speed in hertz. So as the voltage goes up, the speed goes up, voltage goes down, the speed goes down. And when I get close to 0, the motor actually shuts off. There's the dead zone, and you'll see it right around here. Yeah, there it is. For voltages between -1 or -2 and +2, the motor just stops. The reason for that is motors have back EMF. The back EMF limits the current. No back EMF, you get a huge amount of current, damage the motor. So this one is set up, the ECE controller is set up so it cannot supply, will not drive the motor for voltages less than 2. If I then copy that data and plot it, here's what it looks like. This is the speed versus voltage. There's my dead zone. And it's pretty much just proportional. So I can kind of tell you what the voltage ought to be for a given speed. Its speed is 175/5 times voltage, with the dead zone, and corresponding code. Okay, so let's apply a step input. I'm going to take the input and apply a 2.5 volt step, then a 5 volt step. Let's see what happens. In terms of code, I'm going to run for 10 seconds. Let's see. For the first 5 seconds, I'm at 5 volts out. Next 5 seconds, I'm at 10 volts out. Display the speed. Set the direction just like before. Display, time, voltage, and speed. And here's what it looks like. So there's, at 5 volts, it spins at 86 hertz. 10 volts, 172. And if you notice it didn't do that directly, if I plot this data, it's easier to see what's happening. When I tell it to go 5 volts, actually did 5, it kind of ramps up, then runs at a constant speed. We go to 10 volts or 5, ramps up, goes to constant speed. That slope is called the slew rate limit. That's actually probably good. AC motors cannot suddenly change in speed. If they break synchronous speed, torque goes to 0. So if I wanted to change the speed, I've got to let the motors build up inertia, slowly speed up. That slew rate's kind of necessary. That's built into the ECE controller. Alrighty, suppose I want to control the speed of the motor. Well, what I could do is do a search, have the voltage integrate the difference between my desired speed and actual speed. And if I'm going too slow, raise the voltage, too fast, drop it. So to do that, in code, what I do is have where's the voltage? There's my desired speed. It's either going to be 50 or 100 hertz. The voltage that I apply is right here. I have an integrator. I'm going to take the difference between the desired speed, actual speed, and integrate it. This is numerical integration. And just have the voltage being I. This is 0 times VFF. We'll talk about that in a sec. Here's what that looks like. The columns you see on the bottom, this is time, desired speed, actual speed, and voltage. Now, voltage I don't really care about. I just care about speed. With the integrator, I tell it to go at 100. It goes to 100. And what the integrator does is it searches. What voltage do I need to maintain the two? Tell it to drop that back down to 50, integrates down. Plot the two together. You kind of see what's happening. So the red line is my desired speed, the slew rate limit. The blue line is the actual speed. And it's tracking. Make the input a sine wave, and it tries, but there's a time lag. Well, I know what the voltage should be. I know speed is 5/175. Well, I know the relationship between speed and voltage is this equation. So if I know the desired speed, I know voltage I should apply. That's called feed-forward control. Ideally, I don't need this. If I get this correct, I've got the voltage and I'm correct. If I'm a little bit wrong, the integrator should take up all the slop and fix it. Well, if I try that, go into here, I know the desired speed, I know what the voltage should be, plug that in, plus add the integrator to take into account any error. Here's the time, desired speed, actual speed, voltage. Notice it's tracking much, much better. If I plot the two, you can see on a graph, same information, but easier to see. This is part of the reason we like graphs in engineering. The graph is much easier to see than columns of data. It's tracking really, really well. Make it a sine wave input. It tracks almost dead on. That's feed-forward control. This is actually something we cover in 461 Control Systems, a different course. But with Pi Pico, you can implement different types of controllers and control the speed of an AC motor. So in summary, motors with analog inputs can be driven fairly easily with a Pi Pico and a PWM output. The main thing you need is an H-bridge for a DC motor or an ESC controller for an AC motor. Give that and a power supply capable of giving enough power. You're able to control 100 watt, 300 watt, 1000 watt AC motors. And that's lecture number 11 for ECE 476.